A computer processor on its own is incredibly fast, but it has terrible memory. It can calculate billions of operations a second, but the moment you power it down, it goes totally blank. If you run a physical server rack in a traditional data center, fixing amnesia is straightforward. You just physically plug a hard drive into the motherboard. But in the cloud, servers are virtual. Storage has to be detached, distributed, and accessed over a massive network. This physical separation introduces risk. Attach the wrong type of virtual drive to your application, and you could introduce massive latency, blow out your monthly budget, or worse, lose critical user data the moment a server reboots. To prevent that, cloud architects have to balance three competing physical constraints: the raw hardware speed of the drive, the strict permanence of the data, and how easily that data can travel across the network. Amazon Web Services doesn't try to solve this with a single massive superdrive. Instead, they provide a spectrum of highly specialized storage services, each engineered to push against different combinations of those three constraints. Passing the Cloud Practitioner exam requires looking past the service acronyms. You have to logically match the exact engineering constraints of the storage drive directly to your specific application's data bottleneck. Let's start at the far edge of the spectrum, where raw speed is the only thing that matters. Think of an application that needs to process enormous, real-time datasets or hold massive amounts of temporary cache. The solution here is the EC2 Instance Store. Unlike most cloud storage, an instance store isn't floating out on a network. It is a hardware disk physically wired right into the host server running your virtual machine. This chart shows exactly what that physical connection delivers. Looking at the rows for the i3EN metal instances, the random read operations reach up to 2 million IOPS. By keeping the storage local, you bypass network latency entirely. But that localized speed comes with a harsh engineering trade-off. Instance store volumes are entirely ephemeral. If your instance stops, or if the underlying host hardware fails, every byte of your data is permanently wiped out. It makes Instance Store the perfect buffer for processing high-frequency data streams, but a catastrophic place to store your long-term databases. So how do we protect a database from a routine server reboot? We need a system where the data survives even if the host machine dies. To do that, AWS detaches the storage from the hardware entirely, creating the Elastic Block Store, or EBS. Instead of a localized physical disk, an EBS volume is a persistent network drive. You can think of an EBS volume as a giant virtual USB stick. Because it communicates over the network, your server can crash and the data inside the EBS volume remains perfectly intact. You can simply detach it from the dead machine and mount it to a healthy one. However, it can only be attached to one specific EC2 instance at a time. Because it relies on ultra-fast network cables, an EBS volume is physically locked to a single availability zone. If you try to mount an EBS volume located in US East 1A to a server sitting in US East 1B, it hits a hard physical boundary. It cannot cross that gap on its own. To move data across those boundaries, you have to create a snapshot of the volume. You can then package your operating system, software, and configurations into an Amazon Machine Image, or AMI, which acts as a portable template you can deploy into any region. EBS grants your data permanence, and AMIs grant your server configurations portability. But because EBS volumes are inherently single-instance drives, they become a massive bottleneck if you want to scale a web application globally. That leads to our ultimate scaling challenge. What happens when your application grows so large that hundreds of independent virtual servers all need to read and write to the exact same files at the exact same time? Single attachment EBS volumes fail here. Instead, you need the Elastic File System, or EFS. It's a fully managed network file system specifically engineered for massive Linux fleets. Unlike the strict single-zone limits of EBS, EFS is designed to be shared. It automatically scales its storage capacity as you add files, naturally expanding outward to serve hundreds of different instances spread across multiple availability zones simultaneously. And if you aren't running Linux, AWS offers Amazon FSx. It performs a similar high-scale sharing function, but it's highly specialized for Windows Server environments and high-performance computing clusters. To achieve this massive synchronized accessibility, EFS intentionally trades away the raw, localized speed of an instance store and costs more than a standard EBS volume. But it ensures a massive web fleet stays perfectly aligned. Getting legacy enterprise systems into this ecosystem requires heavy lifting. To move massive amounts of on-premises data directly into these specific storage classes, architects use AWS Data Sync to automate and secure the migration. Once in the cloud, you have your spectrum. You have the raw, forgetful hardware speed of the instance store, the single-user persistence of EBS, and the highly available multi-zone span of EFS. Real-world architecture pairs these precisely. You route temporary data processing to an instance store. You anchor your core transactional databases to persistent EBS volumes, and you host your shared content management systems on EFS. If you misalign them, like forcing EFS to act as a localized high-speed cache, you will cripple your application's response time and waste thousands of dollars in unnecessary infrastructure costs. That is the core of cloud computing. It requires looking past the individual tools and mastering the delicate balance of speed, permanence, and scale to engineer a truly resilient system.